Welcome, everyone. Let's go ahead and get started. I'm gonna give everyone the opportunity to settle in.
Yeah.
My name is Raphael Stern. It's my distinct pleasure to be hosting our Warren Lecture speaker today. There we go. Welcome, everyone. It's my distinct pleasure to be hosting Professor Henry Liu today. I printed out his bio because there's a lot. There's a couple of things that he said are very important, or at least one, and that is that he wants us all to know that he was here before he was at Michigan. So Professor Henry Liu is the Bruce D. Greenshields Collegiate Professor of Engineering, the Director of Mcity at the University of Michigan, Ann Arbor. He's a professor in civil environmental engineering, a professor in mechanical engineering, and a research professor at the University of Michigan Transportation Research Institute. He also directs the USDOT Center, or USDOT funded Center for Connected and Automated Transportation. Like I said, he has a long history with this department, so I'm thrilled to be inviting him back here to give his Warren Lecture. Thank you, Henry.
Thank you. Good morning, everyone. Thank you very much for the invitation. It's distinct pleasure for me to come back. I still remember I was teaching in this room for 3201, the introduction class, and I feel come back home, and thank you so much. What I'm going to talk about today, and by the way, Minnesota always has a special place in my heart. So what I'm going to talk about today is safety assessment for highly automated vehicles. This is a topic I've been studying for the last 10 years or so, right after I moved to Michigan. And so, and when I started in Michigan in 2014, at the time, Michigan was doing two things really attracted me. One is that we started, at the time, just started the so-called safety pilot model deployment project. At the time, we were instrumenting about 3,000 vehicles, connected vehicles, and also 20 some of the intersections. And that was one of the big project at the time that was really interesting to me. The other one was the construction, the design and construction of this Mcity test facility, which I'm going to talk about today, and really focusing on safety assessment of highly automated vehicles. So let me talk a little bit in terms of the two research centers I'm hiding right now. One is we call Mcity. It's really a research center under the College of Engineering at the University of Michigan. And it's also a public-private partnership. We work over the years, we work more than 100 companies. And these companies contribute through their membership and to fund research at the University of Michigan. And this is, we're ending the third term right now. Every 3 years of the term, we're going to start a new term this year, July. And also we have, as Raphael mentioned, we have the Center for Connected Automated Transportation, which started really 2016, and as a University Transportation Center, a Region 5, which is the Midwest region. And I'm pleased to say that 2 years ago, the center got renewed, and now University of Minnesota is part of the center as well. So CCAT includes 6 Big Ten schools, and Minnesota is one of those. And so as I mentioned, we work with a number of companies, and then obviously working with the government, and then Minnesota is here. And so we have two pots of money. One is from the industry through Mcity public-private membership. The other one is through the CCAT USDOT funded center. And so we do research, fund research through both centers. And then we instrument the labs. And our lab has two. One is our test facility, the test track for autonomous vehicles. And we're also instrumenting City of Ann Arbor. And so as I mentioned, we instrument 3,000 vehicles at the time, and then some 20 some intersections. Now, because of the FCC ruling, we're re-instrumenting those. And so we're going to instrument 75 intersections, and it's in the process right now for the City of Ann Arbor. And then for both centers, obviously, being at the University of Michigan, we have an education mission, And so we work with startup companies to educate, to have internships for undergrad and graduate students as well. So Mcity test facility, it was designed in 2013. I was one of the designers. It was built solely based upon Michigan DOT's funding. And then all of the equipment on the facility was donation from the industry. So the total, we got total funding for the facility was $12 million. And it was opened in 2015. When it was opened, it was the world first dedicated proving ground for highly automated vehicles. And I believe until now, we're still the most advanced test facility for automated vehicle at the moment. And I'm going to talk a little bit in terms of our development. So my talk today is on safety assessment. So I want to bring you back in terms of the sort of the history, last 20 years in terms of autonomous vehicle technology. And it's really started in 2004 with DARPA Challenge for autonomous vehicles. And then a few teams participate, and particularly Stanford team at the time in 2007 was the #1 team, and then was sort of like acquired by Google to start with this Google X project and building autonomous vehicles. And so that's where the industry really started to pick up in terms of this technology. And then the peak of this technology development is roughly around 2016, when a number of companies, including GM, Ford, and Google, they all announced that by 2020, they will have mass productions of autonomous vehicles, and then these autonomous vehicles will be running on the road. And obviously, we are 2024 now. We don't see any autonomous vehicle as a consumer product. And so 2022, you see this Fortune magazine article, a long cold winter is ahead for autonomous vehicle technology. And then particularly last year in San Francisco, Cruise Automation, one of GM's subsidiary company, and they have this terrible accident occurred on the street of San Francisco, and following that, they basically shut off all their operations in terms of testing, and that was October last year. And that was sort of really the bottom of the, this technology development for autonomous vehicles. And just a few days ago, Waymo, which Google's autonomous vehicle division, and they announced they will be launching paid robot taxi in Los Angeles, and this is also a milestone for them. And then at the same time, Cruise Automation come back, say we're going to restart the testing process, but with a safety driver inside of these vehicles. So you can see, if you look at it in terms of Gartner's emerging technology curve, 2009 is where this technology development started as a consumer product. 2016 is probably at the peak. 2023 is roughly at the bottom. And we're seeing a little bit moving up in terms of the technology development. And so we still have a long way to go in terms of technology development, but I'm seeing the recent progress on artificial intelligence, and it's really up and coming. Okay, so over this process, what really happened? Why is that? And so the main concern is really the safety. And if you look at it in terms of human drivers' safety performance, and in terms of fatality rate and accident rate and things like that, it's roughly around 500,000 miles, or in an urban street will be a lot less in terms of accident rate. Well, if you look at it in terms of autonomous vehicles, because we do not have large-scale deployment, we don't really know. But there are data related with so-called disengagement rate. What that really means is if you have safety driver inside of the vehicle, when your autonomous system doing things you don't feel comfortable, these safety drivers will take it over. when you take it over, is a disengagement of the autonomous system. And so you look at it in terms of disengagement rate as an indicator of the safety performance. Right now is roughly around 10,000 or 20,000 miles. And so it's much lower in terms of the safety performance comparatively to human drivers. And if you look at in terms of, there's some other data as well. Waymo and Cruise, these leading autonomous vehicle companies, they all have studies in terms of their vehicle safety performance. And they are, arguing, say, our safety performance is much better than human drivers. And there's counter argument in terms of why they are still lower than the human drivers. But anyway, I think the message is that there are still major concerns on their safety on the autonomous vehicles. And so, so then why this thing is so difficult? By the way, globally on this technology, up to, in the last 20 years, the investment from industry on autonomous vehicle technology globally is about $160 billion. So there's a lot of money being spent on this technology. So why is so hard? So I summarize this into, I call two curses for autonomous vehicle. One is what I call curse of dimensionality. So what it really means is that the driving environment for autonomous vehicle is very complex. So if you look at it in terms of different weather conditions, for example, right now we have snow, and different road infrastructures, and more importantly, different road users. And each user has distinct behavior choices in terms of their maneuvers. If you combine these things together, the decision variables for this to describe this environment is so big. And so that in order to collect enough data, it takes a long, long time. So that's where curse of dimensionality occurs. The good news is somewhere around 2013 also, this deep learning model was developed. The model became very big, and so that they can accommodate these complex, large amount, massive data. And that's why at the time, people feel confident. In a few years, we already solved all the scientific challenge. It's become really engineering development. So that's why they said in 5 years, we're going to have mass production of autonomous vehicle. Well, in the process of their sort of scaling up in terms of this engineering development, there's another scientific challenge popped up, which I summarize as what I call curse of rarity. What it really means is that not only this environment is very complex, more importantly, these so-called low probability safety critical events is very difficult for deep learning models to handle. I'll give you one example. This is on Google's, Waymo's website. And so you have an intersection, and there's a green light for autonomous vehicle. So the autonomous vehicle has the right of way to pass the intersection. But at the time, cross street has an emergency vehicle coming, turning left. You have to be able to detect there's a vehicle coming, turning left, and that's emergency vehicle has the right of way. You have to yield to that vehicle. This type of situation doesn't really occur that often. However, if they make a mistake, then this might result into a safety critical situation. And that's what happened for one of the accidents for Cruise automation when they deployed last year. So that's why these low probability events, safety critical event, is very difficult to handle for these deep learning models. And then the way to overcome this in terms of data collection is dramatically increased. So the deep learning model can handle 99.99% of the driving situations, but that 0.001% is really difficult to overcome. And so if you look at in terms of methodology-wise, in theory, why is that? So for deep learning models, you're really just trying to train these parameters, right? So you look at a large amount of data, you train these parameters, let's say these parameters are theta, coming from this data and follow this distribution of P. Now you have within this data, most of the data, 99.99% of data are normal driving data. Only a few of these, very low percentage of data are safety critical data, which really contribute to the policy gradient of these deep learning models. So when you train this model, if you put all these data together, if you put all these data together to train these models, the variance for these parameters after training is so high, they didn't really learn anything related to safety critical situation. So that's why the deep learning model, they sort of solved curse of dimensionality problem. The traditional wisdom related curse of dimensionality is being pushed away. However, they have real difficulty to handle these rare safety critical events. And even worse, these two are on top of each other. We still have this complex driving environment. Now you also have these very low probability safety critical event. The current deep learning model cannot handle this type of situation. So that's where the difficulty is. And this curse rarity problem is not only occurs in autonomous vehicle development in terms of the perception, planning, and prediction models. It also occurs for safety validation. Even we want to validate the deep learning algorithm or the autonomous vehicle algorithm. And so if you look into how we validate before these autonomous vehicles deployed on the road, there's really just three methods for us to deploy, to evaluate. There's simulation method. There's test track, for example, Mcity test facility, and also on road. So basically, you just drive your vehicle on road. But if you just drive your vehicle on road, 2016 also, Rand Corporation has this paper on transportation research part A to demonstrate, if you want to demonstrate that the autonomous vehicle safety performance is better than human drivers, and in terms of fatality rate, you need to drive about 5 billion miles. 5 billion miles. So even you have a fleet of something, it drives hundreds of years. So that's why the curse rarity pyramid in terms of the whole autonomous vehicle development process, we have to overcome this in order for us to deploy this. Okay, now in the following, I want to see how curse rarity really impact safety testing, not the development, but testing and the training of the safety for autonomous vehicle is really the two sides of one coin. And so before I look into how we do the testing for autonomous vehicle, I want to sort of formulate the safety testing problem for autonomous vehicles. First, I want to start with this naturalistic driving environment. I was talking about the driving environment, considering different weather conditions and road infrastructure and things like that. Let's just focus on this dynamic element with all the road users. So X is representing each of these vehicles surrounding the autonomous vehicle. And then with different times, with a time dimension, there's different road users. So you have this metric to describe this driving environment. This driving environment has to follow naturalistically what happens in the real world if you want to model this. Okay, so F has to follow this PX. And remember that X is very big. So follow that joint distribution is not that easy. Okay, now if we want to test autonomous vehicle, essentially you let your vehicle out either in simulation or test track or in the real world. You're looking at every round you go, and then you see whether there's an accident happens. Okay, and so essentially doing Monte Carlo Monte Carlo on-road, driving simulation or testing. And so if you drive N miles and has M accident occurs, that will become your accident rate, right? So because this cursor rarity, the A, which is the accident, the probability of the accident is very, very low. And this type of situation is very rare as well. And so obviously you need to drive a very large N that then you can get into the statistically significant accident rate. So the way we overcome this is we're trying to utilize the importance sampling. Instead of doing crude Monte Carlo simulation or Monte Carlo process, then we design this new important function, QX. Instead of sampling from PX, which is the naturalistic driving environment, we want to sample from QX, which is the important function. But you want to make sure your QX has a set of characteristics that later on, when you convert back to calculate accident rate, you still have unbiased estimation of the PA, the probability of the accident. And so you somehow have to be able to construct this QX function, the important sampling function, and so that you don't need to sample from naturalistic driving environment. Instead, in sampling from this QX, and so that you can reduce your testing miles. And so luckily, in the last 5 years or so, we've been really just focusing on QX, how we design this QX. So luckily, in the last few years, we designed this function is essentially a combination of the contribution of the data to the policy gradient, which is this portion of it, and then that a scenario probability. And so if you follow that, that essentially can train this neural network much more effectively to learn how to handle these safety critical situations or how to generate safety critical situations so that we can test autonomous vehicle as well. And so that result into our development of naturalistic and adversarial driving environment. This is not only just the naturalistic driving environment, but naturalistic and adversarial driving environment. So really for this problem to solve, we need to handle two issues. One is we need to be able to estimate this unbiasedly. And then in this case, we need to model our naturalistic driving environment and generate realistic safety critical event, including both crashes and also the near misses as well. And then we have to be able to accelerate the process because otherwise it takes too long for us even to run in simulation. So there's two problems we have to handle. So one is the unbiasedness, the other one is efficiency. So I'm gonna go to each of these. And so how we do this is we do not use the traditional simulator or the traditional scenario-based approach. In the practice right now, what they are doing is they're collecting a large amount of data. They look at these near misses, they look at these accidents, they cut a piece of these situation, and then replay those and see how their vehicle will respond to it. And there's a lot of problem associated with this because there's no interaction between the autonomous vehicle with the surrounding replayed sensor data. The other one is that these traditional simulators are all rule-based. They are collision-free. They're not supposed to generate all these accident or near misses. And so you can't really use the traditional macroscopic simulator for evaluating safety of the autonomous vehicle. You can utilize that to evaluate the mobility or congestion and things like that, but not for safety purposes. Okay? And so what we do is we look at, we instrument City and Arbor and trying to grab the data from the naturalistic driving environment. And so we've been in the last few years, we've been trying to instrument these intersections with cameras. Now we have funding to instrument 75 of those. And this is one of the early intersections we instrument. Is a roundabout, is two-lane roundabout, and it's quite high accident rate. It's the most actually dangerous intersection in the county. And this is the intersection I trained my son to drive also. And this is what happens with these four, fisheye, grid smart cameras. And then we do object detection and tracking, superimpose those to Google Map, and has all these trajectories. And the bubble in front of these vehicles are predictions of their trajectories. And more importantly, we capture the near misses and crash data. And so this is one of the collisions we captured. So on the left, you can see that the two-lane roundabout, if you add outer lane, you can turn right, you can go through, but you're not supposed to turn left. And that's where the mistake usually happens. And that's where what's showing this vehicle on the outer lane turning left, then the inner lane vehicle want to get out, and not result into the right angle collision. And not only these crashes need to be captured, we also capture the data for near misses, and the same location, same situation, you can see the near misses occur. And those are the very, very important data for us to learn from these data to generate this type of situation. Now we, with that data, we designed this what we call neural NDE, which is transformer-based a neural network to learn how to generate these trajectories for these surrounding vehicles. And what happens with just training these transformer-based neural network is that you have a very, very high crash rate. It's much, much higher than what's happened in the real world. And that's not going to work for us either. So that's why we designed a so-called safety mapping network. We look at it in terms of what happened in the real world. Some of the safety critical situation, we purposely doing maneuvers and to reduce the crash rate. And then to really satisfy in terms of align with what's happening in the real world. And so after we're doing that, this is what neural NDE is doing, is what's happening in the real world. We can somehow replicate those, particularly to replicate their near miss rate, their crash rate. And this is what some of the crashes occurred in the real world and can be sort of replayed from simulation. Although this is not exactly replay, but it's generated from the simulation model. Okay, and so there's side swipe type of crash. There's the rear end crash. There's different type of crashes, and each type of crash, according to what happened in the real world, will be able to sort of generate that in the simulation model as well. Okay, and so as I mentioned, that's number one, is we need to model this naturalistic driving environment. Number two, we have to overcome this efficiency issue. And so what we have designed is this QX, which is the importance sampling function, and so that we can accelerate the testing process. We essentially, this naturalistic and adversarial driving environment intensify the generation of these safety critical events so that we can test the autonomous vehicle quicker. And so this is actually a picture was drawn by Wall Street Journal after this paper was published, and they were seeing all these bad drivers, generated in a way consistent with the theory we designed, and so that we can unbiasedly estimate in terms of the accident rate. And really, what behind it is a reinforcement learning problem. We're trying to train the surrounding vehicles to generate the safety critical behavior maneuver to challenge the automated vehicle in a way that's consistent with what happened in the real world. Okay, so we're trying to train this vehicle surrounding agent to generate these safety critical situation. And in order for us to do that, we developed what we call dense deep reinforcement learning framework. Basically, as I mentioned, if you put all together in terms of normal driving data versus safety critical data, and the neural network doesn't learn anything. So what we did is we cut the data out from the safety critical data, not including the near misses as well as the crashes. And so we essentially added this Markovan process and only take out the safety critical state. And so some of the data, a large amount of data, is being discarded. And some of the data is being added and reserved in the training pool. And so we use that data to train the neural network to generate these safety critical maneuvers to challenge the automated vehicle. And so this is some of these challenging safety critical situations in the simulation. So the box of the vehicle is the vehicle being selected to generate the safety critical situation. So you can see some of these events happens within the simulation. This is utilizing Kala simulation model to give us the visualization. Then we put it all together into our so-called TerraSim simulation framework. And it's based upon an open source simulator called Sumo. And then we put together the naturalistic driving environment simulator and also the naturalistic and adversarial driving environment simulator all together. So we take out all the behavior model within the Sumo and replace by our own behavior model and run this. And has a set of interface with physics simulator for sensors and also interact with real autonomous vehicles and also to run together with physical infrastructure. And so here's how we integrate this with our physical infrastructure. And so on your left-hand side, this is simulation models. And then the red car is the tested autonomous vehicle. The yellow car are all surrounding agents. And so we have a real vehicle running within the Mcity test facility. And so that you can see from the camera inside of the vehicle. And then, so all of these yellow cars are virtual. And so we feed this information to the autonomous vehicle and then superimpose those to the view of the autonomous vehicle. So from autonomous vehicle perspective, they have to interact with surrounding agents. Okay, so Mcity has a fleet of 5 vehicles. And so all of the vehicle has the same setup in terms of LiDAR, radar, and cameras. And then all installed with robot operating system and also has open source AutoWare autonomous driving systems. So these are all these are open source. And so for the faculty members and researchers at the University of Michigan, they can run these vehicles and make modifications for their own algorithm and test that in this environment. All right, so here's how we do the testing. So this is accelerated, 8 times accelerated view. So the real vehicle is running, and we generate these virtual vehicles, and then have safety critical maneuvers to challenge this autonomous vehicle, and then look at it in terms of how many virtual crashes generated, and that's the crash rate. All right, so 2 years ago, we started this new project called Mcity 2.0. So as I mentioned, Mcity is a physical infrastructure. And so this is from National Science Foundation. They give us about $5 million to develop this digital infrastructure on top of the physical infrastructure. And so, and also make this infrastructure available for remote access. And so for researchers, if you have a research idea, Mcity 2.0 provides you the real world data collected from the city of Ann Arbor. We have a data engine to translate, to convert the raw data into usable format. And we have a simulation environment, as I mentioned, running on the cloud. and then also combine that with physical infrastructure to do the testing. So have the mixed reality environment. And so then the result you can publish and commercialize. And by the way, all of these, in order to protect your IP, you run your own algorithm in your own location. And so only access Mcity facility through the cloud. And so this is the first remote testing we did last November with our demonstration to National Science Foundation. And so this is from Purdue. So a researcher in Purdue, this is on Purdue's desktop, and we run our simulation model on the cloud, and they run their control algorithm from Purdue on their desktop. And then we provide all these virtual vehicle information to Purdue. Purdue generates the control command, come back to Mcity Cloud, and Mcity Cloud will send that wirelessly to the automated vehicle running within the physical infrastructure. And you can see these are the infrastructure cameras seeing these vehicles are running. And these are just some of the visualization in terms of the state of the vehicle itself. And so actually, you can see there's a crash happened, a virtual crash, right? The real vehicle with virtual vehicles and crash, and then this will stop. And so this is our first test, and we're developing 5 use cases. And actually, Zili has one of the use cases we are in discussion. And then we'll open the remote access to Mcity facility October this year. I also want to mention just in a few days, next week, Tuesday, at ITS America annual meeting in Phoenix, we will officially announce Mcity Autonomous Vehicle Challenge, and to use Mcity test facility as well as our simulation models to test decision-making algorithms. So we invited a bunch of teams to join us, and then through Mcity Cloud to test their decision-making algorithm. So they can run their algorithm at their own location so that we don't have access to their IP, but we run ours in Mcity Cloud. And then every week we have a leaderboard and to count the accident rates, and then so that eventually the winners will come back to Mcity to do more physical testing together with our physical infrastructure. Okay, so last thing I want to have a shameless plug that we have CCAT Symposium at the end of May, and actually early bird registration is ending today. So if you're interested to see Mcity facility and interact with researchers within the Region 5, the Midwest region universities, that's a good opportunity. That's also a very interesting set of panels.